We've got two big issues to talk about in this video. One is, how do we get our students to use mathematical models? Sometimes they just want to resort back to calculations, and we want to see if they've made connections into the models that we've been modeling in our class. Second is, how do we get our teachers, how do we get our fellow educators to also use these models with their students? Because we know there is a vertical progression that from class to class, these models can be great right from early, grade school to middle school, right through to senior high school. In this video, we're going to talk about how to do it. Cue up the music. Go. Hey there, Math Makers. John here from Make Math Moments. And if you have not yet subscribed to this channel, hit that button, hit that bell so that you get notified when we have new videos. Like in the intro here, we talked about how do I promote, or how can we promote mathematical models with our students, but also the fellow educators? And we want to share how to do that in this video. And what you're going to see is a replay from a live session, a live learning session Kyle and I did. Kyle, the other half of the Make Math Moments team, did with our Academy members. Every month we hold live learning sessions with our Academy members. And in this particular session, we were addressing this question about how do we help promote models with our students, but also how do we promote models with our fellow educators. So we're going to get right into it. But I want you to watch and see the examples that we give, because there's some really, as I said in the intro as well, there's some really great examples and progressions of multiplying. That's primarily the topic that we talked about, multiplying into distributive property and into algebra and using algebra tiles. So we're going to talk about that, and I want you to watch for it. So here we go.
I think I see a hand up.
I see Karen.
Karen, go ahead. Yeah, dive in.
Yeah, exactly about what you're talking about. So I work with the teachers in my department, and we're at the high school level, and you've made many references to, the area model. And I've always felt like the area model was ideal to use for learning algebra, but I never really connected it to the arrays that they learned in elementary school, because I never really thought that much about elementary school.
Right.
And so I am having a hard time selling teachers. And I watched a lot of the Graham Fletchy's videos about explaining the learning of fractions and the learning of multiplication and division. And I thought those were super powerful, because I could see students who, sometimes we get students from other countries who are way below 9th grade, and we don't offer anything but Algebra 1. Right. So we have teachers who just say they're not there, and it's kind of that deficit mindset, like it's their problem and they just have to get up to speed. So I'm trying to figure out how to shift teachers into, one, knowing and using some of these other modeling strategies, and wondering, when you introduce them to the kids and ask the kids and problems, did you present them to them at first as options, or did you totally let the students bring it in?
Interesting. That's actually a really interesting sort of connection that you've made. And, we're with you. It can be really challenging, especially, John and I come from secondary, and we were those teachers.
Right.
We were those teachers who sort of were like, okay, I don't know what you're talking about, area model, this, that, because we didn't see those connections. So,
totally.
For us, one of the biggest, I think, bridges to helping is teaching through context. And obviously, if we can make it visual, that's always a huge bonus as well. And that's a piece that I think can be really helpful. And even today, I'm going to go ahead and I'll pull up, and John, if I can, I'll share my screen.
Yeah, I think you should be able to. Go ahead.
Okay, so I'll do that. I just got to bring up an image. We were actually doing one of these screener problems we were looking at was actually a quotative division problem. And it was about 80 students that needed to go on a field trip. And they needed to figure out how many vans they needed. Each van could fit 6 students. All right. So it was very contextual, which is really helpful. And I'm just going to pull up a couple of the solutions that some of the educators shared. And actually, I should also mention that even us as educators, a few of us made small little errors that we realized after. So we noticed them, we named them, and we addressed them. So I'll address those in a moment. But here is one of the solutions that was shared of like a student. I'm picturing this guess and check student, that was already shared. Like that student might approach it this way and go, okay, well, if I just do like, 6 at a time, 6 per bus, I can essentially draw this array all the way until I get to 80. You can see there's 13 rows of 6 and 2 extra. So very quickly and very visually, you can see, okay, like that makes sense. Not super efficient. Like we're not, like loving that from the efficiency side of things. However, we need to obviously acknowledge and really celebrate that student access this task despite potentially not knowing, say, the algorithm or something similar. And then another student did this. This was another educator, I should say. And actually what I want to do is I'm going to open it up because I want to open the other one up as well. So let me do that. So that one's open. Let me open this one as well because I want to see these side by side here. Let me open and preview. That'll help. Okay. So there we are. And I want you to pause for a second and I want you to like have a look at these and like, I've got this one over here that doesn't seem as efficient. This one seems more efficient. And I'm wondering like, can you see the connection between them? And this might be a question we would ask our students in our classroom. Like I've got one student who drew out 80 dots, right? Spent time doing that. I have another student who did this probably much more efficiently, much faster or quicker. And I'm wondering, like, is there a way that these students could maybe see eye to eye, that like actually their approaches aren't all that different? I'm going to give you a little bit of time here. And then if we have a brave soul who wants to raise a digital hand, that would be awesome to share with us. What do you think?
Melanie's raising her hand.
Oh, awesome. Go ahead. Actually, I see Ashley's got a hand up. Go ahead there, Ashley, if you want to turn on, then we'll go to Melanie
Diane
next.
As well.
So I immediately see that those 2 students could have the conversation that at 10 buses, they would fit 60 kids. And so they've got like the student who mapped it all out 6 by 6, he can go to his line 10 item and see that he's at 60 kids there, whereas the other, and see that it's a big bulk of his students, which is the same modeling that the other student's doing as well.
Yeah, I love that. So it's like finding these ways, and this is sort of an example of what we were saying about emerging new models and new strategies. Like if we can help that student see that there is like this one little nudge to get them a little bit closer. And of course, that student would probably need to understand their 10 times tables, right? Like, so not necessarily all of them, but knowing how to multiply by 10 to see that, well, wait a second, I can see that those 60 are actually represented right here by these 60 dots. And oh my gosh, look at 3 more buses over here, 3 more buses. Let me get rid of, I can't get to my little drawing tool. There we are. 3 more buses are shared right here. You can actually see this area model being built. And then you see these extra here. And this was that one educator who split this into tenths instead of sixths, right? They were thinking as a decimal instead of.
Kyle, I got a question about this.
Yeah.
It's a question that you ask these educators. They're just kind of like going back to what Karen was talking about, like, how do we get educators to kind of see this and make these connections, but also kind of like, we'll talk them in a few moments too about like, how do we get students to do this? But my question here is, what did you say? Like you led this with teachers today. So I'm wondering, like, what did you say to the teachers to get them to draw the models? Did you say, draw me a model? Or did you just say like what was the language you used? Because they came up with 2 models here that are different, but it's the same. And I'm wondering, like, I know, and I'm sure this is where Karen's coming from too. It's like, how do you get it that's, most of the group would just go like, well, wouldn't I just do this times this and stack some numbers and do some multiplying? Like how do I get teachers to kind of like draw these models?
Yeah, absolutely. And, you know, I find that you have to be creative sometimes in how you do that. I know that some of the language that I use often is like, I want you to convince me. And something that's really important, especially with students. So this isn't just convincing teachers, but also that student in my class that knows their multiplication facts. If I want them to be able to model, because here's the thing, when I go to algebra, I can leverage these models with algebra when things get more abstract, but I can't do it if they aren't able to model it with numbers, you know, like simple multiplication facts like we see here. So even though you might have a student who's well on their way and they know the rules and they're, you know, they're feeling confident with finding answers, if they're unable to model their thinking, this is where we get into this hang up, because I can't just whip out a model in grade 9 or 10 and sort of say, hey, start using this model, because they're like, where did this come from? So we want them to really see this developing. So we could do some of this work even with some of our algebra students. Our algebra 1 students might need this, this practice to model, because the next model that came up in the discussion, which is really interesting, was this. And this happens all the time, where you'll get a student who does it symbolically. And something that's really interesting when you compare it is this symbolic representation is identical to what was done in the area model here, except this particular person actually made an error in their leftover, that 2/10 thing over here. And if you try to get a student to recognize why 2/10 does not make sense in this context, it is so much more difficult to make sense of it here, but it's so obvious over here. So there's a lot of help that we can have. This student that might appear as though they're not very efficient is actually super helpful for you, because then you get to go back to them and you go like, guess what? This student is helping everyone in the class make sense of the area model, and is going to help us make sense of this model over to the far right, which really is just long division. We call this more like a flexible long division algorithm. If you think about it, instead of me trying to figure out how many 6s go into 80, we say, take out as many 6s as you'd like. I'm going to take out 10 groups of 6s. That's what that is right there. Now I can take out an extra 3 groups of 6s. That's it right there. We have 2 left over. I can add these up and then basically figure out my remainder or my fractional remainder, and we're good to go. This essentially right here is at the guts of where long division comes from, but it's so hard to understand if I don't understand this or if I don't understand that. But when I understand all of these, you're helping everyone. I've got this student here looking back here going, wow, that does make sense. And I have this student looking that way and going like, wow, that symbolic representation actually makes sense too. And you're hoping to be able to nudge students along so that they can represent in multiple ways. And I find when we do this work with teachers, they start to have these epiphanies. They can't just go and do it tomorrow because there's so much work to be done. But if we can get teachers to like see and philosophically connect with what's happening here, and they start to realize that, oh, maybe there's more to this than I realize. Because if I've been teaching Algebra 1 my whole life without an area model, which that was me for like a very long time, then wow, what else is under the hood that I'm just not aware of?
Yeah, like so this is good to see and hear, I think, because what we're seeing here is obviously you're saying, like, we go back to thinking about high school teachers who are like, because I was like that too. I was just like you, Kyle, and I was like, why am I going to use algebra tiles? Why am I going to draw like something called an area model when I could just show these rules really fast and it's faster to learn? Like I skipped all of that. And it used to be in the textbook, right? It would be in the textbook. Oh, you should be doing area models. Okay, skip number 1 and 2 because that's got the tiles. We're just going to go right to the algebra part, right? And it wasn't until I saw this connection to elementary school, to multiplying, and when I started to use it in my class, you're right. I couldn't just go to the algebra tiles or the area model, right away, because it wouldn't make any sense to them. Showing them algebra tiles in an area model at that point is the same as me just telling them the rules of the algebra, because they don't understand the connection, and teachers don't understand the connection either. And I think what I'm hearing from you is what I do with my students. You have to go back to multiplying, and you have to show them how to do a multiplying question with an area model with numbers. And then you can move into why that works with the distributive property, why that works with, putting X's in these spots and multiplying binomials. Like it makes sense only after you show how to draw areas and do multiplying and division that way.
Yeah. And another piece to that I think is really interesting as well is, like, if you think about these problems. So first of all, we solved a division problem. So I think it's important for us to note it's also a specific type of division, which our friends in the Concept Holding Our Students Back course will bump into this as you go. There's two types of division, and this particular type is called quotative division. It's where the rate is known, and we are trying to figure out how many groups. So that is something that's really sort of a big aha moment. But something that's even more interesting to me is that how we typically go about solving a division problem often involves multiplicative strategies. So what I mean by that is, like, we actually use some of the methods we'd use for multiplication rather than using like division by definition. Like, it's very uncomfortable for us to keep removing things. We'd rather add up and get there. So we'd rather actually multiply up. And that's sort of what students tend to do as well. And when you look at this area model, a student could have started with 80 and then taken away 60 and then took away 18, and then they were left with only 2. But in reality, this student probably started by actually building from more of a multiplicative problem. Like, they were probably looking at this rather than it being like 80 divided by 6 students per van. They were probably actually looking at it more like this and saying, you know what, like, how many groups or how many vans of 6 students per van is equal to 80 students. So this says a couple of things. First of all, it shows that students actually intrinsically understand this intrinsic relationship between multiplication and division. But it also tells us that a lot of our multiplication strategies are even helpful in division. So this student probably said, well, wait a second. Okay, I've got some number of vans times 6 is equal to 80. Okay, well, let's start. Okay, if I have 6 students per van, and they're like, well, wait a second. If I know that 10 vans is equal to 60, okay, well, then I know that, wait a second, I have 20 left. So you see this like long division thinking sort of going on here. Okay, well, 20. Okay, well, 6, 12, 18. I know that I could do like 3 more. So there's 3 more vans, and that's going to give me 18. And that, oh my gosh, look at that. That's 78. And then I've got like these 2 left over, these 2 sixths left over to add on there. Now, why I want to share that is because we go, okay, well, if there's 13 and 2 6th vans over here, well, let me think about this for a second. And what I really have, like, let's pretend, let's not worry about the remainder for a second. And let's work with 13 groups of 6 for a second. And let's think about what we really just did here. And what we did was we took 13 times 6 is equal to 80. But really what we did is we decomposed this 13 into 10 and 3, which introduces the need for brackets. So if you have students in your class that, I know I taught order of operations, saying that when you see a bracket, you need to do what's in the bracket first. That was like the rule I taught kids. And it was like, you have to do that. But in reality, my intuition wants me to do the opposite. My intuition says 13 is hard to multiply. I would much rather break up the 13, decompose the 13 into 2. And then it's almost like the rule comes to life, because you can see 10 times 6 and 3 times 6. I can see this 10 times 6 plus this 3 times 6. And right there, you have just utilized the distributive property. When we make this area model, we are leveraging partial products and the use of the distributive property, whether we realize it or not. And then I just think about the implication of like, well, like, let's just imagine that like this was X. Like what changes here? Well, nothing really. The same thing happens. It's like, well, now this is X instead of 6, and I have basically 10X and I have 3X. And I know that that is equal to 80. And I could say, well, 13 X's are equal to 80. And then things start to make more sense to me because it's all connected. Like we started with the division problem. We connected it to multiplication. We showed how, you know, you could even dive in and really look at the long division algorithm and show how that's what you're really doing, or show how you're using partial products, or show how you're using opposite operations, or I should say order of operations. You can make all of this one big connection, which I wouldn't encourage you do with students like this, all in one big jumbled mess. But since we've all been exposed to this, I know that I can take you here and you go, holy smokes, like a lot more of this makes sense than we realized. And to us, one of the biggest pieces is the fact that we can always come back to this context. And we're talking about this in terms of students and vans, so that we can always make sense of the mathematics visually as well as symbolically.
Right. And you said something interesting. It was that, you know, you might not want to do this, all of that with students. And I would argue that you might not want to do that, all of that with a particular grade of students. So for example, is every year in our advanced functions class, which is pre-calculus in the States, we have to divide polynomials. We have to divide, you know, quartic polynomials by linear or quadratic polynomials. And, you know, in my old self would follow the textbook and it would say, you do the long division algorithm to do all of that. Whereas now on the very first day when we do this, I do exactly what Kyle has here on the screen, because I don't know where my grade 12s are coming from. I might not have taught them grade 11. I might not have taught them 9, 10 either. And they might have not seen the area model at all up to that grade. But I go back and we take a good chunk of time and walk through I call it like the history of multiplying and where the algorithms come from. And we do what Kyle has done here, was we show that multiplying is related to division this way. We show that the algorithm is related to the area model this way. And then you can change these things around. And then all of a sudden, when we put X's in them, it doesn't change. The area model doesn't change. The division model doesn't change. The algorithms actually don't really even change. And then we can say, hey, look, we can use the area model. We can use the long division, but we know where they all come from and we know how they all connect. And that's it's one of my favorite lessons, because it's like, you can see kids' eyes go like this. Like they are in their last year of high school a lot of the times. And it's the first time a lot of them have seen this full progression of multiplying and division, stretching back to grade 3 and 4 up to grade 12, of like, all of this has been building towards, you know, maybe for you, this moment where you're going to multiply and divide these complex polynomials, but it's all the same stuff that we did in grade 9 and grade 10. We just, you might not have seen the area model if depending on your teacher, because not everyone wants to venture down that path, but we definitely make sure it's clear. But it's like, to go back to your point, Kyle, is I think it is a huge eye-opening experience if you can show it, especially at the high school level and depending on that grade level, that progression, because you have to show that multiplying. You can't just go to the area model with X's. It doesn't make sense.
Yeah, totally. And as you're talking there, just kind of modeling again, you know, oh my gosh, we had kind of, you know, decomposed one number, and now we've introduced this need for brackets. And then now it's like, wait a second, we could decompose two numbers, and wait a second, what if we didn't know what those numbers were? It was just like an X plus a 3 times an X plus a 5. Oh my gosh, it doesn't really change all that much, because like if X is 10, then it's 100. If it's 9, it's 81. If it's 8, it's 64. If it's X, it's X squared. Right. And like over here, it's like, if it's 10, it's 5 times 10, that's 50. If it's 9, it's 45. If it's 8, you know, you get this idea, and students start to go, oh my gosh, it's like, this will work no matter what. And I don't even have to use this word or acronym, which I taught forever. I said FOIL. And then I wondered why kids got into this big jumbled mess. It's because where the heck did FOIL come from? And I'm like, well, it's the acronym is what you need to do. And I used to tell them, like, just do this and it'll always work. And it's right. It's true. But in reality, this is what FOIL is. This is what multiplying binomials is.
And it only works with two binomials, right? It doesn't work with a binomial and a trinomial, whereas the area model will work. So area model's got, you know, in our class, we say if the FOIL is the four-letter word that starts with F, we're not allowed to say. So, but you have to put money in a jar if you say FOIL.
I love it. I love it. That's fantastic.
Can I ask a question?
Yeah, sure, Ashley.
Of course.
So my wonder is, so I have had the unique experience of going from 5th grade where we push models, like it was most of what I taught was modeling. And now in 8th grade, I'm seeing that my kids have no clue how to draw a representation anymore. So I'm just curious and wondering, what are your suggestions for getting kids back into that? And I don't know if that involves direct modeling, like, hey, we're going to show a model of what this looks like, or
I know Kyle's got lots of thoughts on this, but I was just going to dig a little deeper here before is when you ask kids to solve a problem, like, what are you saying that, and this is what I was asking Kyle before. It's like, what is the language that you're saying to make them go? And maybe also, what are the tools that they have at their disposal that they're just going to go to a calculation, or they're just going to go to like the algebraic solution, and you want them to draw a model, but are you saying draw a model, or are you just saying solve the problem? I'm curious what's happening in your room.
Yeah. So I've used the phrase like draw representation, and I've kind of left it open-ended of this could be a picture that you draw, this could be boxes that you draw. And I do have manipulatives in my classroom, which I never thought about putting those out for use as well during that time. So typically that's my phrasing.
Gotcha. I'm wondering, are you allowing like the tool being like, it's very, very common, right? Like most times, but by the time you get to grade 8, calculators are right there. Are they pulling out their calculator to do stuff like this? Or is it, because I know that Kyle, I wanted to beat him to it, because I knew that he was going to be like, because he always recommends when he works with grade 8 and younger to say like no calculators. Even in grade 9 and 10, sometimes we're going to say no calculators, because the moment you do that, kids are like, whoa. And then they're not sure what to do. And then the multiplying, like, it's almost like it forces the model, because they're not sure how to break the numbers up or break the problem up without drawing something, because they don't have a calculator to rely on.
Yeah. And actually too, like something, so first of all, I want to like congratulate you on the language, because that's really important. You want to make sure students, know that that's what, you're looking for, and that you're promoting this idea. The one challenge we run into, and it sounds like you're bumping into this as well, is that the area model isn't something that students just sort of like land on themselves, right? So it's like, you had mentioned about explicitly modeling, and I would say finding a way, like whenever possible, to do explicit modeling, but make it come from student thinking. And you'll see this a lot in the problem-based units that we put out in our teacher guides. A lot of times, like, again, we use that word emerging. We want to emerge these models. We don't want to just like hope that students come up with them, because again, it won't happen unless they've already been exposed to them. But through things like number talks, for example, is a great opportunity for you to start in a place where you think students are at least like they feel like they can navigate okay, right? Because if it's too far above them and they don't have the model to help them, then it's a slippery slope, right? So we want to make sure the problem is accessible, which is hard to figure out at first. But again, through working with your students and getting to know your learners, you'll be able to sort of get going, okay, I think they're ready to do this. And then some of the language we use is like, convince me. I think I mentioned that earlier. Like I say things like, I don't believe you a lot, right? So if you want to tell me that, hey, 13 times 15 is blank, you know, I don't really believe you, and I'm not really sure, you know, how do I know that what you're telling me is actually factual? So what we'll try to do is get students to do that. And what you'll see, if I come back to some of these earlier examples that I had shared, is that if students don't have, we'll call them more sophisticated models, like I would call an area model a more sophisticated model, and it's a very helpful model, they might start doing things like creating groups if it's a multiplication problem. You might even notice, though, a lot of students won't even put them in a straight line into an array. They'll just like group them in these random buckets. That is very early developmental modeling of multiplication. Like that's what kids will do in grade 1 if you ask them to make 3 groups of 4. They'll just pile, you know, they'll make like circles and they'll pile, you know, the quota in each one. And that's totally cool. In those early grades, we want to start promoting students into helping them make it into rows and columns and help them to see, wow, like, look at that. I could take that rectangle and do this. And it's like, it's still the same amount. Like this is all work we want to do early on. In your case, you probably have some students who are probably able to model with arrays. So you might start there and say, I want you to draw me an array. You might have to redefine it for them if they don't remember. So you're starting there. And then like, as you're drawing, holy smokes, 80 dots, you know, like I'm really making it obvious that this is really painful, you know, like I'm drawing it on the board and the kids are like pulling their hair out. When are you going to be done drawing these dots? And then that's when you're like, boom, stop. I wonder if there's an easier way, right? And it might start with some students saying, hey, well, like, what if we just made like sticks that represent 6, you know? So 6 kids, 6 kids, 6 kids. Great, we could start there. So we do that. It's like, wow, we're still drawing a lot of sticks. Okay, cool. Okay, we could do that a little bit. Then we could be, okay, I wonder, is there another way? Like, I wonder, is there any friendly sort of multiplication facts I can use, right? So now you're kind of pushing them. So I'm kind of modeling, obviously, for multiplication, but this can be done with all kinds of different ideas. And through a math talk where you're facilitating the math talk with a context, and you're having students sort of share, they can solve it in any way they'd like, but when they share how they got to, or arrived at their answer, you're going to try to shape their thinking. So if a student says, hey, put them in these 3 buckets, you might say, is it okay if I represent your thinking this way? And you do it in rows, right? So it's like, can you see your thinking in what I've just done here? I'm like, yeah, like I just explicitly modeled an array. Right. And it's the same can be done for the area model. So that explicit modeling, yes. But what I guess I'm trying to get us to maybe not, you know, to maybe shy away from is like today's note is on area models, you know, like, so copy down an area model is this, and here's an example, and, you know, do this, do that. We want to sort of do it through the problem solving process. And some kids are going to jump right on board. Some students are not. It takes a long time for us to trust these models. And this is why so many students falter when they get to the symbolic representation in math. They don't trust it yet. And like, it's like, that's where they fumble the rules. If they aren't really good at memorizing things, John and I were very good memorizers. So that's what enabled us to, you know, go on and do mathematics. We just memorized everything, but we didn't really trust that it worked. We just trust that the professor knew more than we did, or the teacher knew more than we did. Kids really want to know, like as humans, we want to trust that this is going to work, and that it, you know, you can make sense of why it's going to work. So I don't know if that helps at all, but I want to pause and sort of get your thoughts on that. Like, does that help you with like this idea of how you might emerge some of these models with your students?
Hey, Math Moment Makers. So what you just saw was the video, the clip from our live learning session with our Academy members. And, you know, the big ideas were like, how can we use models with our kids, and how can we use models with our educators, get them to use models more often. Big ideas are like, we got to model that more ourselves. Now, if in that clip we talked about certain tasks that can help with that, and we've got lots of tasks in our academy, and we want to make sure that you know that you can get into the academy free for 30 days if you have not yet done so already. So jump over there, get your free 30 days, get in there, because there's lots of learning to do. And you can jump into our next monthly live session call for free, because you can get those first 30 days for free. So that's it from us for this week. Check out our video for next week. Take care.